right? Up to n, which have the number of particles, and then divided by n, right? So this will be the average velocity. And then you have RMS velocity. So VRMS, this is what? The root, then mean, and square, right? So first thing is that you square. So you have 10 number of particles, V1, V2, and let's say n number of particles. So we square these velocities, right? So we square these velocities and then we take the mean, right? So V1 square plus V2 square plus V3 square, right? And then we take the mean, which is divided by n, then we take the root, right, guys? So this is the root mean square of the velocities. Understood, guys?
Yes, sir.
And then you have what? Then you have the most probable velocity. So let's say the gases, the particle in this gas have, let's say, 3 meter per second, 2 meter per second velocity. Let's say again 2 meter per second, 1 meter per second, and then 4 meter per second. So the most probable velocity will be what? Which have the highest number, 2, right? So which have the highest number, right? Right, guys? So as I was doing, so let's do one problem based on this. So did you understand the velocity is associated with the gas in a container? Right, guys? Did you understand this part?
Yes, sir.
Yes,
So,
sir.
so guys, let's say you have 10 particles, 10 particles with velocity, let's say 8 meter per second, 1 meter per second. You have what? 4, 4, 4, 4, 4, 4, and then what? 7, 7, 6, 5. So these are the velocities of 10 particles in the container. Right. And if I ask you what will be the average velocity and what will be the RMS velocity, and then what will be the most probable velocity. So first, let's say calculate this. So what will be the most probable velocity? Anna, what will be the most probable velocity?
4.
Yes, 4 meter per second. Right. So this will be the most probable. And what will be V average? Abhinav, what will be V average? So V average will be total velocity, right? Up to V10 by 10. So this is what? 8 plus 1 plus 4 plus 4 plus 4 plus 7 plus 7 plus 6 plus 5 and divided by 10. Right. So this is whatever is the number, this is the average velocity. Understood, guys?
Yes,
And,
sir.
and then you have the RMS velocity, right? So how do you calculate that? You square, then sum, and then root over, right? So this will be what? 8, this will be 8 square plus 1 square plus, who has joined? Yes, higher pith.
Good evening, sir.
Good evening, sir. How are you, sir?
Sir, I'm good, sir. How are you?
I'm fine. I'm fine. Yes, so Arpit, today we are talking about the kinetic theory of gases, right? So in the previous, in all the chapters, we studied that we were focusing on only one particle, right? We were calculating the forces, the work done, or anything like that for one particle, right? But in this chapter, you have system of particle, let's say gases, and gases are contained in a container, right? So we have to talk about the cumulative velocity of all these particles, right? So how can we do that? So we can talk about the average velocities of those particles, or the RMS velocity, or the most probable velocity, right? So this I was talking about, and then n and then divide. So this is how much is the velocity, that is the root mean square of the velocity, right? But when you have, let's say, large number of particles in a gas, you can't calculate the right number of particles for gases, right? When you see macroscopically, right? So there are lots of particles. So in that way, you have continuous. You have to look at the continuous systems, right? So Maxwell was the guy who gave the velocity, or the probability density distribution of those kind of gases, right? So those we call the Maxwell distribution for the continuous system. So Maxwell distribution, right? So you guys understand about the RMS and the average and the most probable velocity. Did you guys understand that and understand that part? Any queries? Hmm?
Understood, sir.
Right. So the Maxwell distribution, if you have some continuous system, the number of particle is very, very large, right? So the number density that Maxwell gave was this. So you don't have to remember this, right? So this was what? M by 2 pi RT power 3 by 2, and then you had v square, and then exponential minus of m by 2 RT, and then v square. Right, so this is the Maxwell distribution of gases contained in a container, right? And what are the associated velocities that we have to find? We learned about the discrete system, and we calculated the most probable velocity, the average velocity, and the RMS velocity, right? So now we will again calculate these. So for the case of Maxwell distribution, how is the RMS and the average and the most probable velocity is defined, right? So the average velocity is defined like this. So this is some notation, Kedra notation, right? And the average is defined like this. So you have dn by dv, right? And let's say you have dn, the probability, right, and the average, and then dn, right? So this is how you define the average. So this is the average velocity, right, guys? And then what will be the, okay, who left? What will be the RMS? So RMS is defined like this, right? So this is 0 to infinity v square dn, right? And this is what? Dn. So you know this integral will be what? Dn, right? So you have only calculate, you'll only have to calculate dn by n, right? So this is the RMS velocity, right? And what will be the most probable velocity? So most probable velocity is what which have the highest number of velocities, which is recurring many times, right? So we have to find the maxima, right? Maxima of that point. So to calculate that, we have what? So dn by dv was what? This was 4 pi n, and this was m by 2 pi rt, right? And this was 3 by 2, and then you had v square, and then e minus m by 2 rt and v square, right, guys? So are you guys noting it down? Huh?
Yes,
Yes.
sir.
So if I move ahead, then you can stop me and say that I didn't like that part. So I can scroll back and then you can write. So this part you wrote, right?
Yes, sir.
Okay. So we have to calculate the most probable velocity, right? So we will differentiate this term with respect to dv, right? And find the critical points. Right. How do you find the critical points? I have talked about this in the equilibrium part, right? So you calculate with respect to V and then put it to what? 0. Right. That is how you find the critical point. Right, guys? Remember. So whatever the velocity will be, that will be the most probable velocity. So let's try to calculate that. Okay. So D, we have to calculate D by dV of dn by dv. Right. So this will be what? 4 pi n are the constant term. This is also the constant term. 3 by 2, right? And this is the functional term, v square e minus m by 2 rt. Right, v square. So this is, we have to put it 0, right? So this becomes 0. So this we have to calculate d by dv. Right, guys? So this will be what? This will be 2v e minus of m by 2 pi rt v square, right? And then plus of this guy is left. So we will apply the product rule, right? U and v. Right. So v square is left, and then the differentiation of this will be what? This will be exponential of minus m by 2 rt v square, right, into minus of m by rt, and then v square differentiation is what? 2v. Right, guys? Am I correct? Am I correct, guys? Arpit, am I
Sir.
correct? So,
Yes, sir.
so this guy cancels out, 2v cancels out, right? So we are left with what? 1 and then minus of m by 2 rt v square, right? This is 0. And what is this velocity that we are calculating? We are calculating the critical point, so that will be the maximum velocity, most probable velocity, right? So not the maximum, but the most probable, right? So we have 1 equals to m by 2 pi rt, and this is v most probable velocity. So this will be what? Vmp will be 2 pi 2 rt. Where did I get this by? So 2 rt, right? So 2 rt by m and root over. Right. So this is the most probable velocity for the what? For the Maxwell distribution. Right. Understood, guys? Any question? Guys, any question? Guys, any doubt? Anyone who can respond?
Sir.
Arpit? Yes. Yes, Anna. So this is the most probable velocity for the Maxwell distribution, right? And here R is your what? The gas constant, universal gas constant, right? And this is related by the Boltzmann constant, right? So when you divide this number by the Avogadro number, right? And then when you divide this molar mass with the Avogadro number, right? So you will get the mass of the each molecule, this M, and this will be what? 2 kT by, right? So most probable velocity is what? 2 RT by M, or you can write 2 kT by small m, right? Understood, guys? And now we have to calculate the what? What was remaining, guys? What is remaining? Guys, help me, please. If you guys don't respond, then hello.
Yes, sir.
Yes, sir.
Sorry, sir.
Yes, so we have to calculate the average velocity, V average, and the VRMS, right? We calculated the most probable velocity for the continuous system, right? So in the Maxwell distribution, what was the probability density? This was the probability density, right? 4 pi m, and then m by 2 pi RT, and then 3 by 2, and then v square exponential minus of m by 2 RT, and then v square, right? So this was the Maxwell distribution, and as I already told you, what will be the average velocity? The average velocity, which is defined like this, is 0 v dn by n, right? 0 to infinity. Right, so as you can see, the integral will be, and I leave it to you guys. I will give you a hint. Oh, so let me do one part and then I will leave to right. So yes, so this will be what? This is V, and so this is 4 pi n m by 2 pi RT 3 by 2 v square exponential minus m by 2 RT, and then v square dv. Right, this is the horrific looking integral. Right, right,
Yes,
guys. And
sir.
trick is that we know this integral. So 0 to infinity x to the power m e to the power, let's say alpha, let's say minus alpha x and n, right, dx. So this type of integral you will get as n factorial, and then m plus 1 by n gamma function, and then alpha m plus 1 by n. So this is the value of the integral. So I will leave it to you guys, and this 4 pi 4 n 2 pi RT 3 by 2, yes, and then this integral will be what? VQ, right? E to the power minus of m by 2 RT v square, right? dv. This is the integral, and your n is here, so n cancel. So 4 pi m by 2 pi RT 3 by 2 0 to infinity v cube, and then let's say this is alpha. So alpha and v square dv. So this is exactly looking like this, right? And when you solve this, you will get your, so this will be your final answer. Pi m, right? So this is your V average. Right, guys? Or do you want me to calculate this integral? What should I do? Anyone? Anyone? Please tell, should I solve this integral or move on? Because the integral is not important. The final result is important for the what entrance for this NEET exam point of view, right? So don't
Yes,
bother.
sir.
Yes. So
Okay.
yes. So V average will come out to be what? 8 and then KT by pi m. So always take care of this guy. So whenever you have the gas constant, then you have the molar mass. Whenever you have the Boltzmann constant, when you have the mass for the each particle, right? Keep in mind the average, the VRMS. So this will come out to be 3 RT by m, right? Remember in your VMP, you had only 2 RT by m, no pi. Then we have V average, which is what? 8 RT by pi m, right? And then we have V RMS, which is what? 3 RT by m. So in the case of average only, you have this pi here, right? So these are the three velocities you get for the Maxwell kind of distribution. So you have some gases, and they are some continuous distribution. They have some velocities. Particles have some velocities like this, which are given like this from the Maxwell distribution. And then you calculate the average, the most probable, and the RMS velocity, right? So the important thing to remember for this Maxwell distribution are these three quantities. That your most probable velocity will be what? This will be 2 RT by m. Your average will be 8 RT by pi m, and your VRMS will be 3 RT by n. So can you guys tell me which one is the highest? Which one is the highest number? 2 RT by m, 8 RT by m, or 3 RT by m? Anyone? Arpit, which one is the highest?
ERT by
Yes, 3 RT by m. Who said that?
me.
Okay, yes, Sanya, right. Yes, so when you, yes, so VRMS is higher. VRMS is the greater one. Then we have V average, and then we have V most probable. So that is how the velocities are, right? And when you plot the graph of dn by dv and 1, so this will, so in the x graph you have v, and in the y component you have 1 by n dn by dv. So this behaves like this, right? And this point will be which velocity? So this is the highest number, highest probability, right? Highest probability you already know. So this will be which velocity? Can you guys guess? This is the highest probability. So this will be which velocity?
VRM.
V most probable velocity, right? So this has the highest number of probability. You saw from the discrete calculation, right? That whichever has the highest number of velocity, that was the most probable velocity, right? So in this system, 4 has the had the highest number. So this was the most probable velocity, right? So similarly, whichever have the highest probability, that is the most probable velocity, right? And then you saw that which was the largest velocity? VRMS was the largest one, right? And then in the middle, you had the average. Right. Understood, guys?
Yes, sir.
Yes, sir.
Okay, so this graph represents this probability and the velocities of this Maxwell distribution, right? And when you have only the dn by dv graph, okay. So when you have the dn by dv graph, and when you calculate the area under dn by dv graph, so that will give you the number of atoms or the molecules or the gas, right? So let's say you are given some and for the case of dn by dv and 1 by n, so when you calculate versus the velocity graph, so area under this graph will be 1. Area under this graph will be 1. Why? Because area under dn by dv graph is n. So n by 1 by n by n will be 1. Right. Right, guys?
Sir, can you explain this again?
Right. So when you have this dn by dv graph, right? So let's say this is the probability graph, right? dn by dv 1 by n. So this is the probability, and total probability should be what? Total probability should be 1, right?
Yes, sir.
So the area under this graph will be 1. But when you have this dn by dv only, right? So that will give you, so when you integrate dn by dv with respect to dv, right? And then you integrate, so you will get n, right? So this will give you the total number of atoms. Understood?
Yes, sir.
Okay. So let us do one question based on this. Let's say that you have this kind of graph. This is 2 meters per second, and this is 4 meters per second, right? And this point is A, right? And this is which graph? This is 1 by dn by dv graph, right? So if they are in this question, they are asking about what will be the value of A, right? And you know that you know that this is 1 by dn by dv graph, dv versus v graph, right? So what will be the area? What will be the area under this curve? Guys, what will be the area of under this curve, this area of this trapezium? What will be that? This is 1 by n dn by dv graph versus v graph, right? So area of this graph will be what? You already know. We discussed here. So 1 by dn area will be what? 1, right guys? Okay, so we calculate the area, which will be what? This is A, right? And this is 2. So this will be half of A into 2, right? And this is what? This is 2 and this is A, right? So this area will be what? 2A, right guys? And we know what will be this area? This is 1, right? So this cancels. So this 2A, A is 1, and we know A is 1 by 1. Right, guys? Any confusion, any question in this part?
Also,
Right. Okay. So let me do one problem that I wanted to do. Yes. So this problem. So you have, I will give it to you guys. Please try. So you have dn by dv is what? 3n naught by what? V naught cube. These are constants. And v square, right? And if I ask you, so this is not the Maxwell distribution, but some distribution, right, guys? This is some distribution of the velocities of the gases, right? And if I ask you what will be the average velocity? What will be the average velocity? Can you guys calculate and tell me? So what did I tell you about the average velocity? Average velocity was right. This was the average velocity, right, guys?
Yes, sir.
Yes. So practice this question, right? Let's move ahead and you guys practice this question. Okay. So in the next part, I wanted to talk about the degrees of freedom associated with the system of particles, right? So we talked about the velocities of the whole system, right? The average velocity, RMS velocity, and the most probable velocity. Now we will talk about what is degrees of freedom. And why? Oh, so, but let me, before I go ahead. So this was the graph of Maxwell distribution, right? So what happens when you change the temperature? Let's say this was at temperature T. So when you increase the temperature, what will happen? So for the increase of the temperature, as you saw that for the RMS or for the most probable or for the average, the temperature goes like this. Am I right, guys? Am I correct? So V average was what? So this was half, right? And similarly all the others, right, guys?
Yes, sir.
So for the when you increase the temperature, so this will behave like, so this will decrease, right? So this is, let's say this is T1 temperature and T2 temperature, right? This has been asked in some in your previous year's paper. So that is why I was telling you about this, right? So how temperature dependent is your Maxwell distribution? Velocities. So temperature dependence, right? So T or T2 is greater than T1, right? And this is which velocity? For T1, this is which velocity? Can you guys tell me?
VM.
Yes, VMP. And when you increase the temperature, the VMP shifted to this one. Right. So your VMP is increased, right? So you can see from here that it is increased by T half. It was directly proportional to temperature, right? Right, guys? So this is the
Yes,
behavior.
sir.
So this is the behavior when you change the temperature, when you increase the temperature, this peak point will be get lower, but the velocities will be increased, right? So this is what I wanted to say. And what is the mass dependence? So as you saw see that this is inversely proportional. So this will be like this. So let's say this is one, and let's say this is. So if I ask you which one has the greater mass, which one has the heavier mass, this one or this one? And I am saying that this is inversely proportional. So if your velocity is increased, which means that your mass will decrease. So which here you see that your velocity is increased. So this one is, let's say this one is M1 and this one is M2. So which one is correct? Which one is correct, Sanya?
First one.
Yes, so this mass is higher one, right? This has the lower velocity, so this mass is higher, right? So you are correct. Okay, now let's move on to what we were talking about, the degrees of freedom. So any question up to this point?
No, sir.
Right. So as I was talking about the degrees of the freedom. So it is the number of the independent parameters, parameters that can be associated with the motion of the particle, motion or the energies of the particle, right? Associated with the motion or the energies of the particles, of the atoms, or whatever you see, right? So there are mainly three kinds of degrees of freedom. One is the translation. Translational degrees of freedom. This is denoted by DOF, right? And the other one is the rotational, as the name suggests. And the third one is the vibration. right? So what is the translational degrees of freedom? Let's say you have a point here in the coordinate system. So this is X, Y, and Z, right? So you move this particle here, right? So this is called the translational degrees of freedom. So you can you can move this particle here in X direction, in Y direction, or in Z direction, right? So this is called the translational degrees of freedom. Okay. And then you have rotational degrees of freedom, right? So for the translational degrees of freedom, what are the energies? So for the translation degrees of freedom, you have kinetic energy, which is half mvx square plus half mvy square, and then half mvz square. So this is the translation kinetic energy. And then you have the rotational kinetic energy. So this is how much? So this is half I omega x square, and then half I omega, let's say this is x and this is y, and then you have half Iz omega z square, right? And this vibrational energy depends upon the temperature. So when you have the high temperature, then the kinetic energy and the potential energy associated with this degrees of freedom is called the vibrational degrees of freedom. Understood my point? Guys, understood?
Yes, sir.
Okay, so how many types of particles or the atoms do we have? So we have what? Monoatomic. We have diatomic. We have triatomic. And in the triatomic, we have what? Two, linear and non-linear. And then we have polyatomic. Right, guys? So what are the examples of a monoatomic gas? What are the example of monoatomic gas? Hmm? Neon, right? Neon, argon, or whatever, xenon. These are monoatomic gases, right? Right, guys? And then we have diatomic gases, which are O2, Cl2, and then what? Br2 and rest. Right. So these are diatomic gases. And then we have triatomic, which is what? CO2 and others. So CO2 is and non-linear, which NH3, right? So this is NH2. Right, so this is a non-linear example of triatomic gases. And then you have polyatomic, which is CH4 and some others. Right, right, guys.
Yes, sir.
Yes,
So,
sir.
so for monoatomic gases, can you have a rotation? So let's say you have a point particle, can you rotate it? Well, will there be a meaning of rotation? No, na?
No.
Right. So you can't have a rotational degrees of freedom for monoatomic gas. So let's try to understand what will be the degrees of freedom for these cases. So for a monoatomic and then you have what? Diatomic, and then triatomic, and this is linear. And then you have triatomic, non-linear, and polyatomic. Both have the same degrees of freedom. So monoatomic has translation degrees of freedom. right? And then you have rotation, and then vibration, right? And then you have total, DOF, right, guys? So for monoatomic gas, how many translation degrees of freedom you can have? In the x direction, y direction, rotation is 0, vibration is 0 for low temperature, right? So total is 3 for monatomic gas. For diatomic gas, you have translation degrees of freedom 3, as always. Rotation, let's say this is the diatomic gas. So you can move it in this way, right? You can move it in this way or in this way, right? You cannot move it in this way. So only 2 rotation, right? And then vibration is 0 at low temperature. So 5 degrees of freedom. For triatomic linear, again, you have same. So triatomic linear is what? CO2, right? So again, you only have 2 kinds of rotation, right? And then the vibration is 0. So this is 5. And then you have the triatomic, which is non-linear. Let's say this kind of atom, right? This kind of atom. So in this case, you have 3 rotations, and this is 0. So this is 6 degrees of freedom, right? So these are all at low temperature. For high temperature, diatomic has 2 vibrational degrees of freedom, right? Vibration degrees of freedom. So total degrees of freedom will be what? 7 for diatomic, for high temperature. Right, guys? So did you guys note it down? Guys, did you guys note it down?
Yes, sir.
Yes. So any question in this part?
No, sir.
Right. So why is degrees of freedom is that much important, right? It is important because of the law of equipartition of energy. So what does this law says? This says that for each degree of freedom, you have you have 1/2 RT per mole energy, kinetic energy, or you have 1/kT per molecule kinetic energy associated with it. Right. So your energy will be what? Half RT or half kT. Right. This is energy per mole, and this is energy per molecule. Right, guys? So let's say for ideal case, for ideal gas which doesn't interact with the other atoms, so their potential energy is 0. So for ideal case, for ideal gas, PE is 0. So your E will be the kinetic energy. So kinetic energy is for every degrees of freedom. Let's say you have F degrees of freedom, right? So for ideal gas potential, so the total energy, internal energy will be internal energy. For ideal case will be only the kinetic energy, which will be what? F R T by 2. Right, guys? So your U is what? NFRT by, right? Because for each degrees of freedom, you have half kT energy. So for F degrees of freedom, so for F degrees of freedom, you will have how much energy? FRT by 2, right? FRT per mole. So for N moles, this will be what? NFRT by 2, right? So this is the internal energy for ideal gas with the help of law of equipartition of energy. Understood, guys? So just remember these 2 points, that your internal energy will be what? NFRT by 2, where your F is what? The degrees of freedom. So if I ask you what will be the internal energy for the monoatomic case, for 1 mole, what will be the internal energy? For monoatomic case, what will be the internal energy, guys? Arpit?
S
Yes, yes, what did you say? So for
FRT by 2.
yes, so for a monoatomic, what was the F? F was 3, right?
Yes.
So this will be 3 RT. Right. Write it as 3 T by 2 A for each molecule. Right. So this is similar to what you have learned in your chemistry classes, 3 kT by 2, right? For monoatomic gas. Understood this part?
Yes, sir.
Okay, so the next part that I want to talk about is the specific heat capacity. So why am I talking about this? Because this is related with this. So firstly, I talk about the Maxwell distribution, right? And then we calculated the velocities we associated with it. And then we learned about the degrees of freedom, right? All the degrees of freedom, translation, rotational, or vibrational. And then we calculated the internal energy. With degrees of freedom. And now this internal energy is going to be useful for this specific heat capacity. Right, so specific heat capacity. Right. So what is it is denoted by S? So this is so the amount of heat you need to raise the temperature of the system of the gas by 1 degree, right? And this is about the some kg of that gas, right? So let's say you have some per unit kg of that gas. So for 1 kg, you provide some heat, and then you change the temperature by 1 degree. So this is called the specific heat capacity. Understood, guys? So this is the heat, right? This is the mass, and this is the temperature. Right, guys?
Yes, sir.
Okay, and did I miss? So your gas constant is related by the Boltzmann constant, right? And how it is related by the Boltzmann constant? So K is R by Avogadro number, right? So this is how and this is always also denoted by Kb, Boltzmann constant. Right. So your Boltzmann constant is who is leaving and joining? There must be a connection problem. Okay. So this is how the Boltzmann constant and the gas constant are related. Right. Then you have the molar heat capacity. So molar heat capacity is defined like, so in here you had per mass per kg. For this case, molar heat capacity, you will have what? Per mole. Right, guys? Is it okay, guys?
Yes, sir.
Yes. So now we will talk about some processes. So your molar heat capacity is dependent upon some processes. So let's say if you are working in one processes, then the molar heat capacity will be one thing. And when you change the process, then your molar heat capacity will change. Right. So as you have learned in your chemistry class, one is what? The molar heat capacity at constant volume. Right. And then the other one is the molar heat capacity in constant pressure. Right. So did you learn this in your chemistry thermodynamics part? Right.
Yes, sir.
Right. And how this molar heat capacity is related? So Cp minus Cv is R. Right. Right, guys. Right, guys.
Yes, sir.
Yes, sir.
So your PV is what? Delta Q by N delta T at constant volume. Right. This will be your molar heat capacity at constant volume. Right. And you already know that for ideal case, your delta Q for constant volume. So this is du plus P delta V. This I will talk about. This is which thermodynamics law? Can you guys recall? Okay, so when I will talk about the thermodynamics, then I will talk about this. So let's take it for granted as it is for now. And when we will talk about the thermodynamics, then you will learn that your first law of thermodynamics is this. Right. So you are working in constant so your delta V is 0. So heat is internal energy. Right. And you already calculated the internal energy. This was what? Harpit, what was this? For the degrees of freedom, you already know. So what was this? Sanya, what was this?
NF.
Yes, NFRT by 2, right? Am I correct?
Yes, sir.
So delta V will be delta T. So this will be what? NFR delta T by N delta T. So this will cancels, N cancels, and you will have what? FR by 2. Right, guys?
Yes, sir.
And so what will be the molar heat capacity at constant pressure? So you know that Cp is Cv plus R, right? Right, guys? So you know Cv is Fr by 2 plus R. So this will be how much? Fr plus 2R by 2. So this will be what? Rf plus 2 by 2. Right. So CV is this. Why am I talking about this specific heat or specific at constant volume or pressure? Because this is related with this F. F is your degrees of freedom, right? And we have already learned that for monoatomic, this is what? 3. For diatomic, this is 5. For triatomic linear, this is 5. And for triatomic non-linear, this is 6. And we are at low temperature. Right, guys? Right, guys?
Yes, sir.
Yes. Oh, so I wrote CV. This is CP, right? You guys didn't correct me. So CP. Right. And one more thing is the atomicity of the atom, right? So atomicity of the atom or atomicity of an atom or molecule, let's see. This is defined like Cp by Cv, which is gamma, right? So what is the Cp? What is happening? Why? Who is okay? Many people have left. Okay. Yes. So what is Cp and what is Cv? Cv was Fr by 2, right, guys?
Yes, sir.
So now let us calculate what will be the atomicity of a monoatomic molecule, right? So a monoatomic molecule. For monoatomic molecule, we want to calculate atomicity, which is Cp by Cv, right? And for monoatomic, we know what is F, 3. So Cp is what? Cp is 5R by 2, right? And Cv is what? 3R. Right. So we will have 5R by 2 and then 3R by 2. So R by 2 cancel. So we will have 5 by 3. Am I correct, guys? So
Yes, sir.
for monoatomic, you have this atomicity, right? And can you guys calculate it for the diatomic? For diatomic, it will be what? Please calculate and tell me the answer. Please calculate. I have written the degrees of freedom for diatomic, right? So I have done this. I have done this. Let me. Yes.
Sir, is it 7 by 5?
7 by 5. Okay, let us check. Who has got 7 by 5?
Actually forgot to.
Yeah, I also got 7 by.
Yes, so majority decision 7 by 5, correct. Right. Okay, and let us calculate for what? For the triatomic case. Triatomic and then linear. Right. So this will be what? Please calculate and tell me. So I wanted to do which question? Hmm. Yes, so this, did you guys calculate? So this will come out to be the same as, right? We don't need to calculate. The degrees of freedom are same, right? Right,
Yes,
guys?
sir.
Yes, sir.
So for the triatomic non-linear case, calculate. So in question, they will write like this. So they will write like there is an atom argon, and then they will ask you to calculate the atomicity of argon, right? So you will have to remember that argon is monoatomic, right? And let's say they give you nitrogen gas, and then they will ask you what will be the atomicity. So you will understand that this is a diatomic molecule, right? So this is how you will identify, right, guys?
Yes, sir.
Yes. So what did you guys find? What was the answer?
4/3.
4/3. Okay, so who has got 4/3? One more person 4/3, then we will. Okay, anyone else got 4/3?
Yes, sir, even I got 4/3.
Yes, right. So 4/3. Okay, so this was about the kinetic theory of gases. Do you guys have any question? What did we learn so far? We learned about for discrete systems. For discrete systems, we learned about the average velocity, the most probable velocity, and the VRMS, root mean square velocity, right? And then we talked about the Maxwell distribution. In Maxwell distribution, what was the Maxwell distribution? So Maxwell distribution was defined like this, right? And in the Maxwell distribution, we found out the most probable velocity, which was what? 2RT by m, right? Which is also equals to 2kT by m, right? And then we calculated the average velocity, right? This was what? This was 8,
8 R.
right, 8RT by pi, right? Which is also equal to 8kT by pi. And then we calculated the RMS. What? This was 3RT by. So I'm repeating this many times because only these part are important. They only ask you about these, right? And then we learned about the degrees of freedom, right? That there are 3 degrees of freedom: the translational, the rotational, and vibrational, right? And we also learned that law of equipartition energy, that for each degree of freedom, your kinetic energy was what? K3 by 2. And then for F degrees of freedom, kinetic energy was FKT by 2, right? And we also calculated the internal energy of the ideal gas, which was found out to be what? NRTF by 2. Right, and then we calculated what? The specific heat capacity. One was the specific heat capacity, which was what? Delta Q by M delta T, right? And then we calculated the specific heat capacity, which was N delta T, right? And then we calculated this, which was what? This was FR by 2. And then we calculated molar heat capacity at constant pressure, which was, right, guys. So this much, and then we calculated all the atomicity, which was Cp by Cv, right, for all the cases of mono and di and triatomic gases. Right, and then we also learned this relation. Right, so this completes our kinetic theory of gases. And in the next class, I will be talking about the thermodynamics, right? So thermal properties and the thermodynamics, in which I will talk about the work done in some processes, let's say isochoric processes, isobaric, isothermal processes, and then what? And then I will talk about all those Charles law, Boyle's law, and all of these things, right? So do you guys have any question up to this point? From today's class, do you guys have any question?
No, sir. But sir, can you tell me from which topic most questions can come?
Huh? So yes, so kinetic theory of gases have many parts, but this is very important. The atomicity, right? This atomicity is very important, and then this velocities. So okay, so these velocities are important, right? I will in the next class I will do more problems on this, right? And then I will start thermal properties, right?
Okay, sir.
Okay, so any question, guys?
No, sir.
What should we do? Because I come, so let me give you one problem. Let me see if there are any problem I have. Okay, so I will do this in the next class because I can't find a more suitable, because this chapter is more correlated